Okay, guys, we're going to talk about the serial dilution, the viable cell count. This is going to have a little bit of math in it, but I'll try to go really slow so that you guys can get this. Now, this really is not going to be something you're going to need for the unknown. So this is one-off lab. Some of them are like that. We want to know how many living microorganisms there are. Now, we have talked, I think, about the, the spectrophotometer, which we talked about. You shine a light through a glass vial containing bacteria. First, you shine the light through a clear glass to get a standard, and then you can shine it through a bacterial sample, and the amount of cloudiness or turbidity is going to give us an indication of how many bacteria. However, that's going to count all bacteria, the living and the dead. And what they're saying here is that sometimes when they test an antibiotic, they want to know, we talked about the death rate being 90%, how many bacteria were killed by it. Or also food safety regulations, health departments have these guys so that they're only allowed X number of bacteria per whatever subunit. And so it's necessary for us to be able to count bacteria. So the spectrophotometer we talked about, it's great, but it counts the living and dead. So what we have is the serial dilution method. I think we have talked about this before, but let's go ahead and go through it. So what I'm going to do is I'm going to fill up several test tubes with 9 milliliters of just a nutrient solution, no bacteria. And then I'm going to take a vial that contains the bacteria and I'm going to put it into the first one. And then I'm going to take some from the first one in the second and the second and the third and so forth. So what we're doing is actually diluting the amount of bacteria. So if I have 9 milliliters of fluid in a test tube and I add 1 milliliter of bacteria, then I have 10 milliliters total. And of that 10 milliliters, 1 out of those 10 is bacteria. Does that make sense to you guys? It's 1/10. Mathematically, you can express 1/10 as 1 times 10 to the minus 1. So I stir this up very well, and then I take a sample from that one and put it in the next test tube. Now, I'm only going to move 1 milliliter of fluid from here to the next test tube. So of that 1 milliliter of fluid, then 1/10 of that is the original bacteria and the other 9/10 is the fluid. So I'm taking 1/10 of 1/10, and that is 1/100th or 10 to the minus 2. I do the same thing all the way through until I get, I can't remember, 10 to the minus 6 or so. We'll have to actually look at this. No, we have eight test tubes, 10 to the minus 8. Although really, to be honest with you, by then you really don't get any bacteria. But in any case, so that's basically the technique that we use. Now obviously we're going to sterilize the mouths of the test tubes when we open them, the same way, flaming the mouth when we first open them and before we set them aside. We're going to shake it up and stir up to make sure we get a good even spread on this, because otherwise we won't get a good sample. And then after this, we're going to take and we're going to each of those test tubes and put a measured amount on a TSA plate. Now what we're going to put is actually 1/10 of a milliliter. We have to use pipettes for all this, guys, in order to get accurate measurements of 1 milliliter and 1/10 of a milliliter. But we're going to put it on the plates, and then we're going to use something they call a hockey stick. In our lab, it's a triangular piece of metal that has it goes up and comes out like a hockey stick as a handle. We use that, and we use it to spread out that 1/10 of a milliliter over the whole plate. And then we, of course, put them in the incubator upside down as always, and let them grow. And then when we get the growth, then we can look at and see what we have. Now, we can only count between 30 and 300 colonies. Anything that is beneath 30 is not significant because it's skewed. Anything over 300 we just say too numerous to count. So as you might expect, when the higher the dilution, the less bacteria. So some of those will fall way below 30. Some of them will go to 0. Matter of fact, if I recall right, most of the time 10 to the minus 7th and 10 to the minus 8 had no bacteria at all. And the 10 to the minus 1, 10 to the minus 2 sometimes will have way more. Some of them just actually are a bacterial lawn. There are no individual colonies. So that's going to be our range. Now, in order to calculate how many colony forming units per milliliter we have, this is our formula. And when I say colony forming units, remember that theoretically we say that each individual colony comes from a single bacteria. Of course, some bacteria exist in chains such as Streptococcus or as pairs, Diplococcus, all kinds of things. So we more or less say the basic functional unit of a bacteria rather than an individual. And what we want to know is the colony forming units per milliliter. So we take the number of colonies that we've counted, say I got 50. The dilution factor, that would be the 10 to the minus, say, 4, times the milliliters of the diluent plates, which remember is 1/10 of a millimeter, 0.1. So you multiply that out, and then you divide it by that number, and that gives us our CFUs per milliliter. However, we're doing something that's basically statistical. Statistics require that we have a margin of error, and we call that the standard deviation. So what I'm going to do is I'm going to take that same number, and I'm going to take the square root of it and divide it by this same number, and that gives me the standard deviation. So let's see, let me try to think. 10 to the minus 2 times 10 to the minus 1, 10 to the minus 2, and I said 100. 100 is 10 to the 2. I can't do it. I can't do it while I'm doing this. Hold on, guys. I get around 1,000 colony forming units per milliliter, and when I did the math. But in any case, and of course we have to do, let's see, I said 100, square root of that's going to be 10, and that's plus or minus about 1/10 of that, plus or minus 100. In any case, that's the way that it's done. So if we were doing this in the lab, we'd use Enterococcus faecalis, normal flora in our bodies. We'd use those pipettes, the hockey sticks, use alcohol in order to, what we'd have to do in order to do this aseptically, those hockey sticks, when I need to dip it in the alcohol, shake it off, put it in the burner to burn all the alcohol off, because alcohol kills bacteria. Let it cool because heat kills bacteria, and then spread it out. And then in between each plate, I'd have to do that in order to keep from messing up my count by introducing additional bacteria. Um, this is basically it. It's not really that difficult. That's probably the most difficult thing, and that's just, honestly, guys, that's just arithmetic. That's not even mathematics. A little bit of statistics, but that, I mean, a square root, that's still arithmetic. So that's all there is to this one. Watch those videos. They're pretty good. Matter of fact, I subscribe to some of these because I like the way that one lady teaches. All right, guys, that's it for this one.